Good morning, everyone. Today, I am pleased to present a detailed exploration of hardware and software architectures of wireless internet. Based on a comprehensive studies by the authors mentioned in the guide number 4, which includes Farouk Haferi and Highlands, which are renowned contributors in the field of wireless technologies and the Internet of Things. The discussion will be divided in two main parts. The first one is the hardware architecture. Second one is the software architecture in the WSN. Let's begin. First one. The part one of the guide includes the hardware architecture in WSN. For this, we have the first point is the classification of the nodes by function. You know, in WSN, nodes are not homogeneous. Rather, they are classified according to their role in the network. So we could have the sensor nodes. These are the core components that collect real-world data, such as temperature, humidity, light intensity, vibration, or pressure. We have as well the actuator nodes. These nodes receive processed information and perform physical actions like opening a valve, sounding an alarm, or adjusting light. Next, we have the relay nodes. They extend the communication range to the network by formatting packets from node to node, forming multi-host paths. And finally, we have the sync nodes or base stations. These are powerful nodes that aggregate data from multiple sensor nodes and transmit it to external systems like cloud servers for their processing. A well-designed WSN balances this role to maximize network lifespan and reliability. Next, we will have the core components for a sensor node. In this case, we can say that a typical WSN node is composed for several essential units. We have the sensing unit, which incorporates various sensors tailored to the application, coupled with analog to digital converters, ADCs, that transfer analog signal into digital data. We can follow with the processing units. Usually, it involves a microcontroller, MCU, like, for instance, an MMC P430, ARM Cortex-M series, or a AVR 80 mega. It handles computation, protocol execution, and decision-making tasks. Following, we'll have the communication unit. In this case, we can have radio modules such as IEEE 802.15.4, which is a compliant transceivers, like the CC 2420. We can have as well the Bluetooth low energy radius of the LoRa transceivers. Next, we will have the power supply unit, most often a lithium battery, but increasingly supplemented by energy harvesting models like solar panels, piezoelectric harvesters. Later, we need to include the memory unit. Typically low capacity RAM and flash storage for buffering sensitive data and storage software programs. These components must be carefully optimized to maintain minimal size weight, and energy consumption. This is the typical architecture diagram that we could have in the normal WSN network. As I say, we can have the sensor, the ADC, the microcontroller unit, the memory. It is complemented by the radio module, and obviously it needs to be supported by the power supply. Next, we have the popular hardware platforms for WSNs. A few platforms have become benchmarks in the WSN research and applications. We can include the TelosB, IEEE 102.15.4 same standard. They have low power consumption. They are fully compatible with TinyOS. And they are ideal for environmental monitoring. We could have as well the MicaZ2, MicaZ modes. Those are versatile platforms used widely for academic research, support low power operation and multiple communication standards. We can have as well the Waspmote. These are designed for smart cities. They are used for environmental monitoring and industrial applications. They could have modular and supports multiple radios like LoRa, Wi-Fi, Zigbee, among others. We also could have the Arduino plus the XB modules. Those are very popular for prototyping, offering somehow affordability, extensibility, and easy of programming. And finally, we could include as well the Raspberry Pi with sensor shields. These are used when higher computational capabilities are needed for the edge processing. We could include as well some consideration for the hardware selection. And in this case, we need to select them appropriately according to the hardware requirements and evaluating different or several key factors like the next ones. Energy efficiency. Since many WSN deployments occur in the remote areas where battery placement is impractical. Energy efficient MCUs and radio are critical. We could have as well include the processing capability because application requiring local analytics, anomaly detection, or preprocessing demand powerful processors. We need to include as well, or we need to consider as well, the memory constraints. For this specific requirement, we need to have adequate buffer size for data storage and program executions without significantly increasing energy consumption. We need to consider as well the communication protocol compatibility, as we need to be careful in matching the radio to the protocol needs. 6B for mesh networking, LoRa for long range, low bandwidth communications, BLE for mobile interactions, etc., etc. And finally, we need to consider as well the physical robustness of the solutions. These devices are intended for industrial and outdoor and must tolerate temperature extremes. They must tolerate as well humidity and sometimes refrigeration. The second part of the phase involves some software architectures in WSN. So for this, we need to include the specialized embeddment operating systems. And you need to consider that unlike traditional systems, WSN nodes require extremely lightweight, high-efficient operating systems. Prominent operating system choices include this one: TinyOS, which practically it is an event-driven operating system, highly modular. It is written in NES-C, designed for severe memory constraints. Typically, the footprint is 400 kilobytes. We could have as well the Contiki operating systems, which support IPv6 over 6LoRaWAN. It supports as well dynamic loading and unloading on programs. Lightweighting, preemptive multi-threading via proto threads. We could have as well the RIOT iOS, which is an operating system real-time capable, multi-threading support, post-complaint, excellent for heterogeneous sensor networks. We could include as well the FreeRTOS, which is highly efficient, task-based real-time operating system. And this one is used for slightly more powerful embedding. In particular, we have some key features of the WSN operating systems, but our robots WSN operating system should provide these main features. Low power management. It could include sleep modes, wake on radio, and aggressive DOT cycling capabilities. We need to include as well scalability because they need to support tens to thousands of nodes without architecture bottlenecks. We need to include as well the lightweight network stacks. For example, the Contiki stack allowing even 8-byte microcontrollers to implement IPv6 communications. We need to include as well the dynamic curve of operating. Some operating systems allow over-the-air updates without physical access to nodes. And we need to include as well the modular software architecture, which is essential to minimize memory footprint and allow reconfigurability. Obviously, we need to consider some factors of choosing operating systems, like resource constraints. We need to consider as well the available RAM, the flash memory, and processing capacity. The network requirements to support mesh routing protocols like RPL, routing protocol for low power and loosey networks, IP connectivity, and ad hoc routing. One of the key questions is, do we need or don't we need real-time requirements? Obviously, with the application demand deterministic response times, sometimes RIOT is preferable. And we need to consider as well some programming model sustainability, like event driving, like the TinyOS versus multi-thread, like real programming styles different. Define the selection. The design and implementation of wireless sensor networks hinge upon a meticulous choice of both hardware and software architectures. A carefully selected server node platform ensures operational longevity, robust performance, and cost efficiency. And obviously, an appropriate chosen operating system empowers the WSN with efficient communication, scalable networking, and energy conservation mechanisms. Within this era, where IoT and WSN are increasingly pervasive, expanding smart cities, precision architecture, industrial monitoring, and healthcare, a profound understanding of this architecture is not only beneficial but essential for engineers and developers. So, with this knowledge, or with this foundational knowledge, we can start now, or we are equipped now to proceed with the design simulation and performance evaluation of the WSN tailored for specific application requirements. These are the references that include the document. You can rise within the learning guide number 4. Okay, this is the step number 2 of the guide, hardware and software selection. In this point, I will present and explain the hardware and software selection for my wireless sensor network project, aligning these requirements with energy efficiency, modularity, and network scalability. This selection is directly linked to the application problem defined in phase number 2 and the architecture and protocol chosen in the past phase. So, for hardware architecture, we have chosen, or I have chosen, a configuration based on 3 types of nodes. Sensor nodes. These nodes are responsible for monitoring environmental variables such as temperature and light. They collect data from their surroundings and transmit it to other nodes. The relay nodes, these nodes extend the coverage of the network by forwarding data packets from sensor nodes toward sync. And sync node or base station, this is the most powerful node. It collects all the data from the network and interfaces with external systems, such as cloud databases or data analysis servers. These are the basic components for each type of node. Every node, regardless of its function, shares a common hardware architecture. A sensing unit, in the case of sensor networks, includes sensor connectors to an analog to digital converter and for capturing physical phenomena and converting them into digital signal. We have a processing unit based on the Texas instrument named CP430 microcontroller, responsible for managing local operation and decision making. A communication unit uses a CC2420 radio transceiver compatible with the IEEE 802.15.4 standard, which ensures reliable and low-power wireless communication. We have as well the memory unit, consisting of 10 kilobytes of RAM and 48 kilobytes of flash memory. A node to store sensor data and operating code. And finally, obviously, we need to include the power supply based on the standard AA batteries. So adaptable for energy harvesting system in for the platform, we had selected the TelosB, and these are the reasons why we have selected that. I have selected that for the ultra low energy consumption, which is critical for maintaining the functionality over months of years with it has also full compatibility with this IEEE standard, enable robust multi-hub wireless communication essential for wide area deployments. I have chosen this one as well for the integrated environmental sensor for light and temperature, reducing the need for additional sensor attachment. Obviously, with this sensor, I have extensive support in research and industry, providing access to many tested examples, protocols, and tools. Now, regarding the software, I have selected the Tiny operating system for several reasons. This operating system is specifically designed for wireless sensor network, particularly for high resource constrained devices. It uses an event-driven programming model, which means nodes only can consume power when specific events occur, ensuring extremely low energy usage. It provides modular support for communication protocols such as collection fee protocol, CTP, for energy or efficiency routing in multiple networks. It enables aggressive duty cycling to maximize the battery lifespan of the devices. TinyOS is lightweight, modular, and has a proven track record in both academic and real-world deployments. By combining TinyOS with the TelosB, we guarantee a network architecture that is not only energy efficient, but also scalable, reliable, and cost-effective for a wide variety of application domains. Obviously, it is compatible with MATLAB array-based performance analysis. Okay. Simulation. I handle the simulation using MATLAB. I'm very comfortable with this program. Obviously, you can use another tool. I will try to present the complete implementation of the wireless sensor simulation and AI-based analysis. This step connects directly with the high-level requirement required in phase 2 and the architecture access technologies and protocols selected in phase 3. Our workflow is the structure defined in the phase 4 learning guide, covering not only simulation goals, tool selection, environmental modeling, protocol implementation, simulation execution, AI-based modeling, and phase 2 validations. What are the simulation goals? These goals are aligned with the challenges identified in phase 2 and the strategies proposed in phase 3. And these are evaluate energy efficiency, measure per node and total energy consumption across the network to validate the TelosB and the TinyOS configuration supports extended operation with battery depletion. Evaluate protocol performance, assess the multi-hop forwarding protocols effectiveness in delivery packets for sensor up to the scene. Validate network reliability and their interference. This allows us to test the network resilience against obstacles, this is signal loss and random interference. The simulation tool selection, I have selected the MATLAB scene events and the AI toolboxes as our simulation platform. And this choice is justified because MATLAB provides a powerful numerical computer environment suitable for modeling wireless channel effects, energy consumption dynamics, and multi-hop routing behavior. It builds in AI toolboxes. It includes regression learner, classification learner, neural network toolbox. Enables seamless integration of the AI-based analysis directly on simulation data. Additionally, I have included a C++ implementation for cross validation and portability purposes. The WSN environment model, this was modeled with the following characteristics. I have included 20 nodes, 20 sector nodes randomly distributed across a defined aura, the 100 meters times 100 meters. Each node has sensing and transmission capabilities with 5 joules of initial energy and packet sending every 60 seconds. The topology, I have selected a simple mesh topology where nodes forward packets through the nearest network or directly to the same node located to the center of the area. Obstacles were modeled by adding an extra 5 dB loss with interference occurs, simulating physical barriers in the deployment environment. Interference, a 10% probability of extended interference was included, randomly affecting transmission by crescent packing nodes. Traffic patterns, each node generates one data packet every 60 seconds, so represented periodic environmental monitoring. The protocol implementation. The protocol is a basic multi-hot forwarding protocol consistent with the collection tree protocol CTP approach selected in the phase number 3. Nodes send data either to the nearest network or directly to the sink based on distance calculation. There is no retransmission on failure, reflecting a simple energy-aware transmission strategy. The path loss is computed using a path loss exponent of 3, which somehow involves an urban outdoor model with success probability derived with the computed signal at the mention. These are the simulation parameters: duration 3,600 seconds, 1 hour on the network operation. The channel model, I have selected a path loss model with exponent n3 and random interference included or induced obstacle loss of 5 dB. The transmission intervals, 1 packet every 60 seconds per node. The packet size is 4,000 bits per packet. The energy bit transmission is 50 nanojoules per bit, and the reception is 30 nanojoules per bit. The interference probability, 10%, and randomly chosen for transmission. These are the simulation results. After executing the simulation, the following key parameters were captured. Total energy consumed, 18.6 joules across all the 20 nodes. Average remaining energy for nodes is 4.09 joules, approximately 82% of the initial energy retained. Total packets sent, 613 packets successfully transmitted. The throughput is 680 watt bits per second. The average end-to-end delay, 30 seconds, which has been estimated. The packet loss is approximately 10%, and it is attributable to the interference model. The visualizations will include a bar chart showing remaining energy per node and steam flow showing packets sent from mode. These are the analysis and the results. Which is basically what I already said. And this is the A-based modeling, prediction and estimation. Obviously, I have implemented an AI-based component using simulation results as a data set. This AI analysis is aligned with the energy efficiency challenges identified in phase number 2. It has an objective, is to predict node energy consumption and estimate node line time. The tool that I have selected is the MATLAB Neural Learning and the MATLAB Neural Network Toolbox for model training and evaluation. MATLAB was chosen for its seamless integration with the simulation environment, direct use of simulation outputs and training data. Obviously, we need to include the data preparation. The data set was extracted directly to the simulation log. For each of the 20 nodes, the following features were recovered. Input feature, node position, distance to the sink, number of packets sent, number of packets received, initial energy, and interference event encounter. And the target variable, remain energy after simulation, use it to divide total energy. I have run multiple simulations and vary according to random seeds. So we have 200 samples for the data sets. 2 models were used for train and compare. The linear regression, a baseline model to capture the linear relationship between node features, and the neural network, a more expressive model to capture nonlinear dependencies. We have some model evaluations according to these parameters: the root mean square network, the R2 score, the energy optimization insights. So we have these results. And so we have some interpretation of the results, of the AI results. Node placement optimization, the adaptive to the cycling, and the predictive maintenance. So we have some particular elements covering each one of these analyses as well. And here we have the validation on the phase number 2. For all of them, yes, the energy efficiency has been validated, the network reliability has been validated, the scalability has been validated, the data management has been validated. And as simulation, I have included the simulation evidence and some code. Simulating the code for the MATLAB. And the C++ code to compare. The results. And this is the result. Please remember that you can use the MATLAB online tools using the university licensing for this simulation exercise. You have to start your session, set your credentials. That is all from my side. If you have any question, please don't hesitate in contacting me by the Teams chat or by the forum. Thank you very much for revising Keep recording. Have a good day.